Welcome everyone to today's webinar, Strategies for Optimizing FPGA Designs on AMD Versal, Adaptive SoCs and FPGAs. We're thrilled to have you join us today as we delve into advanced techniques and strategies for harnessing the power of the Versal product family in FPGA design. Whether you're a seasoned engineer or just starting out in the field, today's session is really designed to equip you with the knowledge and insights needed to enhance your Versal-based project's efficiency and effectiveness based on our first-hand experience working with the product. Before we begin, let's go over some quick housekeeping items to ensure a smooth experience throughout today's webinar. We will be hosting a Q&A session at the end, so you can submit your questions at any time during the webinar using the Q&A button on your control panel. Feel free to type them in as they arise during the session, and we'll address them later on. Should you encounter any technical issues or need assistance, please send a message through the chat and one of our administrative team members will be here to help you. We're here today to talk about our experience with Versal, but why do we feel we have the authority to speak on this topic? Well, in our first decade, Fidus did a ton of varied AMD Xilinx related work. And so in 2011, Xilinx asked Fidus to become their first ever Premier Design Services member in North America. To this date, Fidus and AMD collaborate closely on opportunities and train together on the latest technologies, all with the end goal of helping our clients get their solutions to market as quickly and smoothly as possible. We also happen to boast the largest team of AMD certified engineers and professionals in North America. So who is Fidus? Well, we were founded in 2001 and we've grown into a 150 plus person, all North American electronic system design and development services company. We serve all industries and markets and have 3 brick and mortar locations, 2 Canadian locations and a US home base in Silicon Valley. We've been working with FPGA sockets since 2002, and it would be safe to say that more than 80% of our projects have included FPGA content. We do an incredible amount of work with AMD products, but also have gold tier partnership with Altera, formerly Intel, and many years of experience with other manufacturers, Lattice, NXP, FNX, to name a few. But we're most proudest of our repeat customer rate. We've got close to 95% of our customers returning year after year with new projects and new business, a real testament to the quality and efficiency of our work in improving our customers' time to market. As a full services electronic systems design firm, our professionals and engineers cover a multitude of service disciplines, including FPGA design, embedded software, hardware, signal and power integrity, ASIC RTL design, and verification. We help our customers by supplying some of these expert skills directly or by managing the complete project from start to finish. So now I'd like to welcome Norman Leclerc, a distinguished senior FPGA designer and team leader with over 2 decades of experience in FPGA design, simulation, and DSP architecture. He's had great experience integrating complex electronic designs and optimizing DSP algorithms with a deep focus on video and image transport and high-speed network infrastructures. He has extensive experience with the AMD platforms such as Vivado and Versal, and is a certified member of the AMD Alliance program. Norman's experience has been crucial in pushing the boundaries of FPGA capabilities and implementing advanced network protocols on FPGA systems here at Fidus. We're grateful to have him here talking about Versal today. So thank you for attending. We hope you find this webinar informative and engaging. Please make sure you post those questions. And on that note, over to you, Norman.
Thank you, Alicia, for this introduction. So here are the strategies for optimizing FPGA designs on an AMD Versal adaptive SoCs and FPGAs. In this webinar, we will go through an example of high-speed data moving application. We will fly by its basic structure and configurations. We will look at the implementation and look at the expected performance of the system. And finally, we will have a glimpse on how we can change the system to work under dynamic function exchange. The Versal adaptive SoCs are a mix of scalar, adaptable, and intelligent engines. They are designed to target a wide range of applications. They have hard and high-speed interfaces such as PCIe, multi-gigabit Ethernet, and memory controllers. And they also have a good amount of IOs. All these structures are distributed around the die to leave the adaptable engine, programmable logic or PL, in the center. This makes the die large, and being so, the scalar engines and memory controllers can be far from the IOs, and the AI engines can be far from the memory. To make things worse, some Versal have a few interconnected dies. They're called super logic regions, or SLRs. So how to efficiently move data from one component to the other when they can be placed on two opposite sides of the SoC? To efficiently move data, the Versal includes a structure within the PL, which is a high-speed network on chip, the NOC. The NOC can transfer data at a frequency of up to 1 GHz, only 128-bit data bus. The NOC has integrated high-efficiency DDR4, LPDDR4 memory controllers, and some Versal will also have HBM memory controllers. It is hardened, therefore is always running at optimum speed, and requires minimal efforts from the place and route engine. The NOC has bandwidth allocation and 3 levels of quality of service. It can generate parity and transfer the poison bit. It can do alternate translation, and for easy connections, the NOC interfaces use memory map AXI and AXI stream interfaces to connect to the attached peripherals. In this webinar, we will be using the AMD VCK190, which is an AI evaluation kit that is for sure on everyone's birthday gift wish list. This kit has multiple interfaces such as PCIe, Ethernet in both RJ45 and SFP format, and HDMI ports in both input and output. It has soldered on 8 GB of LPDDR4 memory and another 8 GB of DDR4 dual inline module. For expansion, the card has an FMC expansion port. The kit targets data centers, radio, automotive, and radar applications. The project we are presenting is an HDMI 2.1 video frame grabber. We wanted to be able to capture 8K video resolution at 60 frames per second, which translates to 48 gigabits per second of video data. We will imagine this system part of a larger design and thus artificially contain it into a portion of the FPGA using a P-block. On the VCK190, we see that the HDMI are connected to the GTYs on bank 106. So we will want to transfer data from this corner down to the LPDDR controller, and we'll use this one. And it's going to be these memories. So we're going to use the NOC to transfer data from the HDMI transceivers here down to LPDDR here. There is a project that we're going to be using. It's an all-IPI design. I decided to do it that way just because it's easier to show. Although you still need the IPI to configure the CIPS and the NOC, you could very well instantiate your block diagram into RTL. It's just that easy to use the NOC into the RTL code. So we have the CIPS, we have the NOC, we have the AI engine, we have the HDMI, the transceivers. I added a video frame buffer writer to transfer the video to memory. We have supporting blocks, clock generation, and reset generation. And we have a AXI Smart Connect. Zooming on the CIPS and the NOC, we see that they share 7 AXI interfaces. We have 4 cache coherent interfaces. We have 1 full power domain interface, 1 low power domain, and 1 for the PMC. We also have the video feed that's coming into the NOC for the DDR memory. On the master side, we have 1 master that's going to be to the engine control, and the other master is for the HDMI frame grabber control. Let's have a quick look at the NOC configuration. For a more detailed description of everything that's going to be here. I would guide you to the PG 313, which is the product guide for the NUC. So configuration opens on the board tab. The board tab has been populated with the board selection, which is the VCK19. Moving on to the general tab. So this is where we select the number of AXI interfaces, slave master, and the number of clocks. We also have the interlock interfaces, which we don't have in our design, so it's 0. And memory controller configuration. And we have a single memory controller with 4 memory controller ports. And we selected the lower base address at 0. Now the input tab, we have to associate each slave AXI to the peripheral it is attached to. So the first one was cache coherent interfaces, so we selected that. The next one was the full power domain interface, which is non-coherent, so we selected that. Then it was the LPD and FPMC, which have their own category, so we selected that as well. And the 7th or 8th input was the video feed, which was connected to the PL fabric. Moving to the outputs tab. So we had the first master, which was connected to the AI engines, which has its own category, so we selected that. And the second master was to the PL fabric, which was the HDMI frame grabber control. Now to the connectivity tab. We have our connectivity matrix. This is where we tell the tool which slave AXI has access to which master. Here, all our interfaces will be able to write to memory. So we selected a memory controller port for each one of them. We wanted the full power domain to be able to control the HDMI frame grabber. So we selected that as well. And our video feed, which comes from the HDMI frame grabber, will only be able to talk to the memory. So it's going to be able to write to memory controller port 1. Now to quality of service. All our slaves will be best effort, except the video feed. We said our video feed required a certain amount of bandwidth, which was 48 gigabits per second, or 6 megabytes per second. So we entered 6 megabytes per second here, and we gave it the priority of isochronous, which guarantees a maximum latency on the bus. Address remap is the address translation. In our case, we don't have any. DDR basic. This is the basic configuration for the clock and DDR controller type. Also, we're using the LPDDR4. Most of the options here are grayed out because we selected the board, the VCK190, and we've told it to use a specific DDR controller. So there's nothing much more to say here. Now let's move to DDR memory. This is where we give all the timings for the DDR chips, and also if we're using ECC memory. Now to DDR address mapping. So here we have 3 predefined address mapping, or we can have our own. Now to the last tab, which is hidden here. DDR advanced, we have more ECC options, refresh options, power saving options, and migration options. All the DDR configurations were left by default. these were configured by the board settings that we selected when we created that project. So we can close this and just regenerate the layout. So let's have a look at the NOC from the IPI point of view. Here we have an unplaced NOC. This is not how it's going to look like when it's going to be placed and routed. But we have the number of NMUs and NSUs that are going to be used. NMUs are NOC master units, or the slave interfaces for the NOC. And the NSUs are the NOC slave units, or the master axis interfaces of the NOC. Here we can select each site and manually place the NOC with lock constraints. We can't move them around, but we can have the properties and manually place them here. I've never had any issue with the tool placing them automatically, but if you want to place them manually, this is where it would be done. So what I did now is I highlighted all the nodes of the NOC to see where it goes on the die. So you see all the structures of the NOC on the die. It's a little messy, so let's clean it up and just get the tiles. So looking at just the tiles, we get a few dots here and there. These are all NOC structures up there too, and also we have the vertical line. So this is how it looks, all the NOC looks on the die. Let's look at our implemented design. Now we have the HDMI frame grabber that is here. Yeah, the CIPS and the DDR controller right here. So of course I constrained the HDMI frame grabber to one part of the chip, doing it on purpose so it doesn't spread around, so that I'm sure that it is as far as possible from the DDR memory, so that I can show that the NOC can move data efficiently with bandwidth allocation. So now let's look at the NOC placed en route. So if you remember, when it wasn't placed, it was looking like this. So now that it is placed, we have our NMUs, NSUs, and DDR controller to the right place. We have the HDMI frame grabber that's about here, and extended here because we have the master interface here. So this is what it would look like. Now let's look at the quality of service that we requested in the NOC QoS. Here, if I bring this up a little bit, we're going to look for our video interface, which is this one down here. So we see that we required 6 gigabyte per second, and the estimate is also 6 gigabyte per second. So this is fine. We see the estimated cycles. So the latency is here. It should always be 72. So this is perfect. And this is the path that the data from the HDMI frame grabber to the DDR is going to take. So we see all the NPSs, or net NOC packet switches, that are used along the way. Going back to the device view, we're going to light up our NMUs and NSUs. So we're going to mark them. We're going to mark the, I have it around here. We are going to mark the NSUs green and the NMUs blue. There we go. So if I zoom in here, I see that I have 2 NSUs and 1 NMU. Going back to the NOC, seeing the disposition is correct. And going back down, I'm supposed to have my 7 other NMUs, which are here. And going back to the NOC, they are here also. To see some connections with the NMUs and NSUs, I'm going to light up some traces. This, and there we go. So let's zoom in here, and we see all the connections going from the NSU to the HDMI frame grabber, and the video coming out of the HDMI frame grabber going to the NMU and down the NOC. Another reason why I wanted to constrain the HDMI into a P block is to enable dynamic function exchange, or DFX, so that this region could be a partially reconfigurable region. I did that in another project. So I did the exact same thing, except that now it's modified for DFX. Now we have 2 NOCs. We have one NOC for the static region, which has DDR, and the other NOC for the PR. So each NOC is connected through an inter-NOC interconnect. If we go back to the initial NOC here, we will see that we actually have, in the general, 1 slave and 1 master interconnect. The master for control, the slave for the video feed coming back. We're going to look at the QS. We don't have any QS, or the QS that we have here, we can't change it. It comes from the DFX region. So if we go back to the design and open the NOC for the PR region, we have our master and slave, slave being the control, master being the video output, and also we have 1 slave interface here, which is actually also the video input. So the video input comes from the AXI slave to the NOC master interface. This can be highlighted in the connectivity. We have the AXI PL going to the master inter-NOC interconnect. And if we look at the QoS, we see that the QoS is on the master interface. We have our 6 GB per second here. So it's a little bit of changes, but everything is handled by the NOC. It's just that easy. Of course, we had other signals, so I had to add some other functions to enable PR, but this is subject of another webinar. In this webinar, we have seen that the Versals are large FPGAs that have an integrated network on chip, the NOC. It can transfer data at high speed between different components. It spans the entire PL region and has multiple entry and exit points. And finally, it can do quality of service and bandwidth allocation. I thank you for listening and hope I have taught you a thing or two. Giving control back to you, Alicia.
Okay, thank you so much for that, Norman. I am now going to bring you to the webinar. Let's see, Norman, hopefully you can turn on your, there we go. There's Norman, and I'm also going to invite Mike Brown to join us, another senior FPGA designer here at
Fidus to answer some of these questions that have come in today. So thank you, Norman, for the presentation. Now, what we're going to do, I'm just going to encourage everybody once again. I have a couple of questions that have come through. However, if you have a question for Norman or for Mike, please do pop it into the Q&A. But I'm going to jump straight into them. So the first one I have here is from Mark S. And either Norman or Mike, I'll let you decide who's going to answer this. But could you discuss some of the challenges you've faced with integrating CIPS, CIPS, DDR, and AI engines within Versal? And how do you recommend overcoming these challenges?
Well, I can start here. Well, one of the challenges was to assign the DDR pins. The NOC DDR interface is using the XPIOs, and you have to properly set the pins. You properly select the pins in the FPGA. That would be one challenge. The other one is more complex, is to know which component of the CIPS you're using and from which interface it talks to connect to the NOC. The NOC has multiple interfaces. It has the cache coherent interface, a non-coherent interface, has a PMC interface. You have to know through which tunnel the communication is done so that you can connect the proper interfaces to the NOC. So that would be the two main challenges I would see.
Mike, do you have anything additional to add on that one?
Yeah, I guess it's a great question. I guess in particular for certain devices, Versal does come in devices that have more than one super logic region, as Norman mentioned in the video. Something that you need to take into consideration there is that can make timing quite challenging, and particularly for signals that are not going through the NOC. So it's important to look at registering those signals that are crossing SLR boundaries.
Excellent. Okay, hopefully that answered the question there. Okay, I've got another one here from Pooja. Can you give me some examples of some strategies for optimizing data transfer across the chip using the NOC? Do you have any examples you could provide of how you have successfully employed those strategies?
First of all, you have to know the traffic you're dealing with. You have to know how much bandwidth you require and how often you require it. For my example that I'm using in the HDMI frame grabber, I mean, the video interface is a periodic signals which has blankings, so it's not constant, but it requires a certain amount of how should I say this, of latency. I mean, you need your video at a certain time or you're going to skip a frame. So that's why I used isochronous. I could have used, for my example, another settings, which is the high priority, sorry, the high priority, but I didn't want to use that because in case we would have another signal that would require high priority, it would pass over the video. But the video, since it has a isochronous latency or a isochronous level of QoS, it would be assured to have a certain maximum latency. So you would have your frame at proper time. So you have to know your traffic, and you play with QoS and probably placement, but then again, you might be stuck with your IO placement. But that's how I see it. You have to know your traffic. That's the main thing.
Mike, anything extra from you, or thank you, Norman?
I guess it is important as well. I think more applicable to larger designs. The NOC resources are finite, so making sure that you understand where you're not wasting those resources. So what you might want to do is like Norman had said, categorize the important high bandwidth, like low latency type traffic, and assign those to the NOC. If you have like some lower bandwidth, something like controller status interfaces, you can still use the general PL fabric for routing that type of traffic and reserve the NOC for the really important stuff in your design.
Okay, excellent. Thank you. Okay, we're going to jump to, we're already over at 12 o'clock. So we're just going to answer one final question from Steve here. It says, when setting the QoS parameters, isochronous you mentioned was used for the video data. Can you explain what this means? And did it change the NOC implementation?
Well, isochronous means that you're guaranteed a maximum latency. So you won't have you won't have a signal that's going to linger in the NOC for forever. So this is why I chose it for the video frame buffer. Like I said, a video frame buffer or video frame grabber, you need your frame at a certain time. So you need to be guaranteed that it's going to be transferred at a certain time. It's not high priority because you might have controlling signals that are more prioritized than the video signal, but you need to be absolutely sure that your traffic is going through at certain time. High priority means that it's going to go over everything. So if you put video there, as soon as it gets in the NOC, it's going to go through, munching over all the other priorities. So it might not be the best way. Best effort, well, if you put everybody high priority, you're going to be everybody best effort. So best effort, you know, it's best effort.
Excellent. Any other final parting thoughts, Mike, from you?
Not on that particular question. No, I think Norma covered everything there.
Okay, excellent. Well, I'm just going to suggest that everybody visits our website at fidus.com/partners/AMD. We would love to speak to you more about any of your Versal challenges. I do see some additional questions just popping through now. We can't answer them all, but we will follow up with you. And you will receive a copy of this recording in your inbox very shortly. So thank you, Norman. Thank you, Mike. We will be back with more Versal content very shortly. Thank you to all.
Thank you.